Okay, well, thank you all for coming in person. Thank you, everyone. I see a long list online. Thank you for joining from whichever time zone you're in. I'm really excited to talk to all of you about my dissertation work. I want to thank my committee for being here, Bill Gay, Mike Zinn, and Rob on the call. Okay, so I'm going to do a little introduction of my last decade of research. I did my undergraduate studies at IIT Madras in India, where I was introduced to human-centered design through building assistive technologies for people with disabilities. And then I worked for a couple of years at Xerox's research lab in India, where I got to witness my research be part of a commercial product. We used web cameras to remotely monitor human breathing. For example, in a baby monitor, you'll see that the remote part and the camera part will come back later in my dissertation work. And for the past 6.5 years, I've been at UW-Madison, and I've had the opportunity to do some really cool things with robots, and I'm going to talk about one part of it today. So the title of my talk is Towards Effective Robotic Groupware. So I'm going to start with what groupware is. Groupware refers to digital tools that are specifically designed to help people work together. This is a term from a research area called CSCW, or Computer Supported Cooperative Work, that specifically studies how technology can support and shape human interactions in the context of us working together. We use groupware all the time to work with each other. For example, Google Docs is a groupware tool that helps us work collaboratively on a document, both synchronously and asynchronously. GitHub is a groupware tool that helps people collaborate on code, and the version control feature on GitHub manages the contributions from various group members to a shared code base. This is a research prototype called Kirigami Table. It is a shape-changing tabletop groupware that supports co-located collaborative work. So in my dissertation, I proposed the term robotic groupware for groupware that is built on robotic technology. I would say that building robotic groupware requires methods and practices, both from the CSCW community and HRI community. In the CSCW community, robots are very rarely used as enabling technologies for collaborative tools. Last year, when I attended the CSCW conference, there was only 4 or 5 papers out of the 250 plus papers that were presented that was at this intersection. In the HRI community, robots are not studied very often in the context of groups. And if you search for human-robot interaction, you will see images like this. And HRI is largely focused on improving the interaction between one human and one robot. And this is what some other smart researchers in the HRI community said at a workshop in the CSCW conference, that robots are not studied enough in the context of groups and teams. Placing a robot in a group setting is a non-trivial extension of individual interactions, because we have to consider the different ways in which the robot will interact with each member of the group, but we also need to consider how the group members will interact with each other and what the robot's role is in this group setting. So robotic groupware sits at the intersection of being complicated for both communities, and that's maybe why there isn't that much work in this intersection. I want to make one distinction at this point. This is a survey paper, very comprehensive one, on the study of robots in groups. And in their inclusion criteria, they say that the robot must be autonomous or perceived to be autonomous, and at least 2 locally present people must interact with the robot simultaneously. But my definition of robotic groupware is more encompassing, and only mandates that the system be specifically designed with the goal of being placed within groups for improving human-human collaborative work. So by this definition, the most prevalent robotic groupware in HRI is telepresence robots. The work in my dissertation focuses on a different, more powerful robot form factor to enable collaboration on more complex tasks. And today I'll be presenting one such robotic groupware system called Periscope that we developed. Today's presentation only covers a fraction of the work that I have done during my PhD, but this work would not have been possible if not for all the other areas of HRI that I got to explore. Okay, so for my thesis statement, as a step towards building effective robotic groupware, my thesis statement is that an effective robotic camera system can facilitate human-to-human collaboration in remote settings that involve physical tasks. The Periscope system, I think, represents a concrete example of such a robotic camera system. I will talk about various aspects of this thesis statement throughout the presentation, and towards the end, I'll bring the slide back up, and hopefully the work that I've presented will provide support for this statement. At a high level, there are three core things I will talk about: the design, the usage, and the application of the Periscope system. And then I'll discuss the thesis statement and future work. Okay, so I'm going to start with the design of the Periscope system. I'll first motivate the remote settings that involve physical tasks, part of my thesis statement. A lot of tools allow us to work remotely, and they're great for on-screen digital tasks like this collaborative whiteboarding task. But it remains really tough to collaborate on physical tasks like this in a remote setting. The challenge in collaborating remotely on physical tasks is because physical tasks require people to look at physical objects from various angles and in varying levels of detail. This is a very natural thing to do in a co-located setting, but how do we support this type of collaboration remotely? Let's consider the scenario where we have two collaborators who are in separate spaces and trying to collaborate remotely on a physical task. We'll call the person who is manually doing the physical task as the worker, and the remote person who's providing them guidance as the helper. Our contribution is a prototype robotic system called Periscope, where we have a camera mounted on a robot arm that helps the remote person view the physical objects in the worker's environment from various angles, and thus effectively collaborate with the worker. This is a video that was recorded from the camera on the robot arm that shows the worker's workspace. With Periscope, my goal was to leverage the capabilities of this very capable robotic arm to provide people with the viewpoint flexibility that they would need to remotely collaborate on physical tasks. So how do we go about designing a system like this? As I mentioned before, we can draw from the relevant background in CSCW and HRI to design such a system. In the next few slides, I'm going to cover some CSCW concepts, and then I'll touch upon the HRI concepts when I present the design. The first concept is of awareness. In collaborative settings, individuals need to create and sustain awareness to determine the current state of work and anticipate future states. These are some elements related to workspace awareness in the literature. These can be about understanding what the worker is doing, identifying the objects that the worker is engaging with, knowing where the worker is looking and what they can see, recognizing the area that the worker can affect change, and an understanding of the past and how an action was performed or how an artifact came to be to its current state. In co-located group work, a lot of these elements are known either consciously or subconsciously, but when designing a remote groupware system, we have to decide whether and how we want to support these elements. The next concept is control mechanisms and control policies to empower users to acquire the diverse and timely information that they need to maintain awareness. Control mechanism is the ability to change the view, and control policy is the decision about who can change the view, when it can be changed, and what it should be changed to. In our case, these control mechanisms and policies associated with the view is actually about robot control, since our view is from a camera on the robot. In the rest of the section, I'm going to present our control mechanisms and policies to support the awareness needs for collaborative work on physical tasks. Okay, so first in Periscope, the helper has the ability to freely control the camera and see things from their desired viewpoint. We draw from the research on robot teleoperation interfaces for designing these interactions. The helper can remotely control the view using simple mouse inputs or button presses on a screen interface. The helper can use a mouse click to look at different objects, then adjust the view to inspect specific objects. Helpers can also annotate the camera feed directly to indicate an object or direction or area. In this video, the remote user is changing the view through mouse inputs, and the arrows and dots that you see correspond to user inputs. The worker also has the ability to change the view to show things to the helper. For the design of the worker interactions, we take advantage of the fact that the worker is co-located with the robot. The worker can control the view using hand gestures or by manually moving the camera through physical contact. Here's a video of the worker pointing to various things in the workspace to change the view, and also using direct physical interaction. So in our system, the worker can move the camera locally, the helper can move the camera using remote control, and because our camera is mounted on this capable robot arm that can move in complex ways, we can provide users with a great deal of flexibility in their views. But I mentioned earlier that the worker and the helper are changing the view using simple mouse and gestural inputs, but this robot moves in complex ways. So how do we map these simple inputs to complex robot motion? For this, we include a set of autonomous robot behaviors that can augment simple inputs from people. These behaviors can reduce the effort that users have to put into changing the view, but autonomous behaviors also take away control from people. Ideally, users should have a high control over the view with low effort. Basically, they should be able to see what they want to see without putting too much effort into the control. And we try to maintain that balance in the design of our user interactions and autonomous behaviors. I'll show a short clip of the track hand behavior. Here we see the worker completing a manual task, and as they're working, the robot automatically keeps their hand in the camera view. To summarize what we've seen so far, we designed camera controls such that the helper and the worker can independently move the camera when they want to. And the robot assists and reduces their effort and assumes part of the workload of camera control. So this sharing of camera control between the worker, the robot, and the helper forms the core of the Periscope system. And we call this approach shared camera control based on a term from HRI literature, where robot behavior is determined by inputs from multiple human and robotic agents. There are several things that we need to consider for the design of a shared control system regarding the contributions of each entity. What is their contribution? How much is their contribution relative to other contributions? When does this contribution happen? And how does this contribution change over time? This should sound familiar to the concept of control policy from the CSCW literature. In the HRI shared control literature, this control policy would be called arbitration. And the design of the arbitration will depend on the context and the task and the awareness needs that we want to support. In Periscope, we designed 3 modes: helper-led mode, robot-led mode, and worker-led mode that distribute the camera control in different ways among the helper, robot, and worker. We have a leader-follower paradigm where each mode is led by one of the 3 entities, while the other 2 exert less influence. So in the helper-led mode, for example, the helper has high influence, the robot has medium influence, and the worker has low influence over the camera view. So what that means in the context of all the capabilities in the system is that in the helper-led mode, the helper has almost full control of the view through the helper interactions. The robot will ensure safety and good camera motion, and the worker can only influence the view using a pointing gesture. With this approach for camera control design, our hope was that different modes would be useful at different points of the collaboration process, and that's what I'll talk about in the next section. I'm going to talk about a lab study that we conducted with 12 pairs of participants who used Periscope to do a collaborative assembly task. I'm going to introduce a concept called shared visual context from early CSCW literature, which is defined as task-relevant visual information that can augment the verbal communication of collaborators. This is an example conversation from prior work where a helper guides a worker in adjusting the inclination of a bike seat. First, the helper tells the worker to adjust the seat so that it's parallel to a bar. The worker confirms, this bar here, is that good? Without the relevant visual information, we don't know what that means, but presumably the helper does have that information. And so they say, angle the nose up a little bit more. The helper uses the shared visual context to gain awareness about the current state of the task and the worker and plan the next steps. The use of this and that is called deixis, and that is highly contextual and would make no sense without this shared visual context. The use of definite articles like the bar and the nose also indicate that the helper and the worker are creating common ground and shared knowledge of the objects in the environment. And this is called conversational grounding. So what we would hope to see is that if Periscope is effective in facilitating collaboration, then we would see evidence of such processes in the conversation data between helpers and workers. The way we designed our study was inspired from a style of evaluation called formative, qualitative, opportunistic evaluation. I'm going to focus on the opportunistic part in this presentation. An opportunistic evaluation is in contrast to controlled. Opportunistic evaluations allow open-ended and natural exploration by users, whereas controlled evaluations have regulated environments that are meant to isolate specific variables for analysis. Our specific types of opportunistic evaluation is called experimental simulation. And in this type of evaluation, you stage situations in the lab that closely resemble the operational context. So in our study, we try to maintain key elements of a natural collaboration scenario within a lab setting. Bless you. And that meant that we had a cluttered 3D workspace and 45-minute long tasks. We provided very limited instruction to participants on how to proceed with the task. So basically, each session looked very different because people decided to proceed with the task in different ways. And most importantly, we did not compel people to use any of the features of the system. They could have chosen not to move the robot at all. And so we asked them to move the robot if they thought it was required for getting the job done. I'm going to explain the study setup and show one clip of 2 participants from the study. We have a worker in a workspace who is completing a manual task. They are co-located with a robot that has a camera mounted on it. This is the remote helper's user interface. The remote helper views the workspace through the camera that is mounted on the robot. On the remote user's interface, we see the camera feed from the robot-mounted camera. There is a 3D view that shows the robot and its surroundings. The worker and the helper can communicate through a video conferencing link. There's a control panel for controlling the robot and hence the camera view. And there's an annotation toolbox to overlay graphics on the camera feed. The local worker also has access to a similar interface so that they can see the shared visual information on their respective interfaces. In the clip that I'm going to show, you're going to see a recording of the helper's UI. What you'll hear for most of the time is the helper giving instructions. You can focus on the camera feed to see what the helper sees through the interface, and also look at the mouse pointer to see what the interactions the helper is having through the interface. So the two people in the clip are trying to build this 3D circuit, and the helper is giving the worker instructions on which part they need next.
So that one, can you show me that piece? Is that just a straight line? Okay, that looks like the correct piece. Can you show me the face of it? Okay. Yep, that's the correct piece then. So now let's get one more. Okay, it looks like you have the other piece we need. It's that blue 2 piece.
Yep.
So those are the last 2 pieces we'll be needing for right now.
We mainly use this type of video data for the insights in this section. We had 12 pairs of participants come in for the study. We treated the first 4 as pilot and analyzed the data of the last 8, and that resulted in about 12 hours of data. It took almost 3 months to organize and analyze this data for 2 people. And we used a tool called Elon to code the data by assigning descriptive labels to different parts of the data. I'm going to show an example of the analysis using a short 15-second clip. In this video, on the left, you will see the screen recording from the interface, and on the right, you'll see a bird's eye view from the workspace.
That's not what we're looking for. I'll go one above. Maybe take that out and show me. Yeah, that's what we're looking for. Okay.
This is a screenshot from Elon for the clip that we just saw, and it starts at the point where the helper says, that's not what we're looking for. We look at different channels of data, like the helpers and workers' audio, their actions, and what they can see on their shared view. Then we write abstract descriptions of what we observe. And this section over here corresponds to the 15 seconds in the clip that you just saw. I'm going to talk about how we get from these abstract descriptions to meaningful insights. So these are the 4 pieces of audio that we hear in the 15-second clip. And these are the 3 relevant data channels. These are the abstract descriptions for the 3 channels. I'm not going to read all of them. When we start finding patterns, we can start to write higher level codes. For example, in this clip, hand tracking was on, and we see a repeated behavior from the worker where they place their hand on the table after an action to maintain the relevant view for the helper. Because the hand is being tracked, if they do any extraneous motion, then the camera view is going to change. So they keep their hands still on the table so that the view stays still for the helper. So that's a very repeated behavior. You can already see there are 2 in this 15-second clip. Then I would assign a higher level code for this, like maybe the worker is explicitly directing the camera view. And then we do this coding for hours of data and start to make higher and higher levels of code based on repetitions across sessions and within the same session. And based on all of these high-level codes, what you will see in the paper is that this 15-second clip is evidence for a use pattern that we call use pattern 5, where the dyad uses the robot-led mode to gather components for the build. This use pattern constituted 17 out of the 20 times that the robot-led mode was used. And then I break this down further. In all cases, we observed that workers explicitly directed the camera by moving their hand to relevant locations, and that's what makes this a unique use pattern. Additionally, when waiting for the helper to give further instructions, workers often rested their hand on the table to maintain a steady view of the relevant area. The dissertation has a total of 20 such use patterns. Really verbose descriptions of each pattern, similar to what I showed before, some aggregate data for each dyad, and a discussion on how these results support or indicate limitations in the design choices that we made in the previous section. I'm going to talk about one main takeaway here related to the shared control design that we discussed in the previous section. We observed two types of shared view control. First was view control within a mode. For example, in the robot-led mode, where the hand tracking was on, the worker could explicitly direct the camera, for example, by resting their hand on the table, and the helper could adjust the view around the worker's hand. One other thing was users influencing the view based on conversation. So, for example, the helper might ask the worker to point at something so that the robot looks at it, and the helper doesn't have to change the view. The second type was the transfer of view control by switching between modes. We saw that dyads switched modes often, and they used all modes at different points of the collaboration process. This is a graph of the number of times each pair used the three modes. Remember that all of these numbers could have been 0. We didn't ask people to use any of the features. So this is data based off natural exploration by users. And these are not just random button presses, because these are all counts from use patterns. So there are specific contextual and awareness needs that these button presses were meant for. So I think our results overall suggest that a shared control approach is important for such a groupware system. We did notice some instances of conflict in the data where the arbitration didn't go as planned, and I'll discuss one such instance later in the discussion. Yeah, and so the final core section of the dissertation work is a second user study that we ran to understand real-world applications where a system like Periscope could be useful. The manufacturing domain is a really promising domain for the application of robotic groupware, because robot arms, like the one that we use in Periscope, are already part of many workflows. Robots are increasingly prevalent and accepted in these domains, and so they can be enabling technology for new paradigms of work. The specific application that I explore in this part of my dissertation is workforce training for physical skills. These types of skills are almost never taught remotely. We have access to a lot of education and workforce training remotely, but physical work is something that is rarely taught this way. And even if it is not necessarily effective. So our guiding question for this part of the work is going to be, what opportunities for the application of Periscope exist within workforce training? We pitched this idea to Boeing, who are already collaborating with my committee members for a very related but different project. And they seemed interested in this idea and gave us resources to explore this. So at a high level, our research methodology was inspired from a human-centered design method called context of use analysis, which characterizes anticipated circumstances of system use. Data for context of use analysis can come from field studies, surveys, interviews, artifact analysis, etc. In our case, we used a participatory research approach where we engaged with potential real-world users of our proposed paradigm, which was remote workforce training. So our participants included engineering students, trainers from Boeing, subject matter experts, and instructors from technical colleges or vocational schools. We also use the Periscope system as a technology probe in our study. Technology probe is an artifact that can provide hands-on experience to examine how future technologies might alter current practices. This method is really useful when you need to envision a new work practice that might be very different from the one that you're used to. So this is an overview of how we apply these methods to engage with different stakeholders across various parts of the study. Almost a year ago, we had a preliminary discussion with the Boeing trainer to understand if our ideas had any merit in the context of Boeing and its processes. Based on that information, we wrote a proposal, which our collaborators at Boeing refined, and they also provided us with motivating examples of where their current training methods could be augmented with new solutions. Then we consulted experts to design our task and scenario for a lab study that we plan to run. In this lab study, instructors from a technical college remotely instructed engineering students using Periscope. We asked them for feedback after their use of the system. And finally, we showed videos and data from these interactions in the lab back to the trainers and our collaborators at Boeing and asked them for feedback on how it was relevant to their processes. Currently, we're synthesizing the data from all these phases, and this is still ongoing work. In the rest of this section, I'm going to touch upon our lab study and some of the analysis. So this was our setup for the lab study. Our remote instructor could go to periscope.cs.wis.edu and log in to our system from their home or office computer. And the student was in our lab, co-located with the robot and a mock car stereo installation setup. It was complete with radio, amplifier, wire routing, power supplies, and all the tools they needed. We had 2 instructors, and they taught 3 students each across different sessions. This image also shows how we ran the study. I was in India or California, and I used Periscope system to run the study. And Nate and I also used it to collaborate on task and scenario design. I actually have a very sped up video of us on a call where we're discussing the layout of the room, and Nate is going to make some changes now. So I'm going to talk about our high-level findings from the study. We still have a lot of data left to analyze, so we'll add to this list in the coming months. So the first thing was that with all the feedback that we received about the task design, we ended up with a blended instruction style. The instruction session was about 40 to 45 minutes, where the first part was an in-person instruction of basic skills by Nate, and then the second part was remote instruction by our expert instructors who helped the students improve on those basic skills and also troubleshoot any problems. I'm going to show a video of one remote instruction session.
And you routed a gray wire through there as well, right?
That right here.
You can strip that one too and hook it up to the other one.
Yeah. It came out, was a little loose.
What's that again?
This one came loose, so I have to put that
Yeah.
back in.
Tighten it, yep. Might as well hit all 8 of those screws. Well, you got your screwdriver out, check them all for tightness, make sure they're good.
So the action that you see the student doing in that video is crimping. He learned how to do that like 20 minutes before in the in-person instruction. And what took 45 seconds in the in-person instruction took the student 25 seconds by the time the remote instructor had joined. This meant that the worker could independently work for an extended period of time. There's a lot more silence in these videos compared to our videos from study 1. And that's because the worker has a higher level of knowledge and is able to do tasks, but they need sporadic interventions by the instructor. The feedback from the instructor to tighten all the screws was very contextual and specific to this student, that they were not mandated to do that. That was in response to them watching the student do something specific. So what that meant was each session with every student for the same instructor looked very different because it was very specific to the problems and the knowledge level of that student. The tasks, we actually introduced problems for the students and instructors to troubleshoot. So they were not routine tasks, so the instructor couldn't repeat the same things that they did in a previous session. Compared to our findings in the previous study, the way people used the system in this study showed both similarities and differences. We observed that many of the use patterns that we had identified in the previous study were repeated here. In this clip that we just saw, we see UP6, where the instructor uses the hand tracking mode to monitor the student's movement as they executed a task. This is a use pattern where the worker does not explicitly direct the camera. For an example of the differences, I'm going to pick the use of the annotation feature. In the previous study, there were on average 32 uses of annotation in a session. And in study 2, we had a single instance of use across 6 sessions. And so that's a pretty stark difference. And we can at least partially attribute it to 2 things. First, in study 1, the worker was mostly seated, while in study 2, the student was mobile. So if the instructor used annotations, then the student would have to make a deliberate effort to access the view so that they can see the annotation. That might have discouraged instructors from using the feature. But second, and this might be more important, is that in study 1, participants were not aware of task terminology. So this red component that you see is a transistor, and most people just called it the red triangle throughout. But in study 2, especially because of the in-person training, students were familiar with relevant processes and terminology like crimping and connectors. So in study 2, the pair was able to communicate.
Oh, that's like one. That's 40. No, that's 40 minutes. 5 minute mark.
Thanks. So in study 2, the pair was able to communicate verbally using the shared knowledge, but in study 1, they communicated more visually and relied on the annotation. Finally, I'll talk about 3 scenarios that we identified where a robotic camera solution could be promising. First is formal schooling. This is workforce training in a technical college or vocational school, which closely resembles our study design and works well with the blended instructional approach. We also talked about the potential for remote students with folks at a community college who were interested in Periscope because they have a course that is fully remote. They already have PTZ cameras for the equipment in their lab, and they thought that remote students would benefit from having more flexible views. The second scenario is in-house foundational training that often happens in specialized industries like Boeing, and Boeing has entire training facilities dedicated to this. If this paradigm of remote training could be extended from one trainer and one worker to one trainer instructing several workers, then some training services could be provided from a central location to a distributed manufacturing system. Also, remote training technologies could allow an aging workforce to remotely impart their knowledge and expertise to younger workers. And the final scenario is workplace coaching. This is a type of trainer at Boeing and is also there in some other industries who supports workers in the production area. They do exactly what our system supports, which is skill enhancement and troubleshooting. This type of training is just-in-time training where workers acquire or refresh necessary skills right at the moment they're needed and in the actual work environment so that it is relevant to the task at hand. This type of support is probably all the more important with the evolving nature of work, with increasing automation. The routine tasks are being automated away, and the tasks that remain and need human intervention are less frequent, but have high skill requirements. So new training paradigms could support these type of changing work profiles. So that concludes this section, and I have a shortish discussion. So here's my thesis statement again. An effective robotic camera system can facilitate human-to-human collaboration in remote settings that involve physical tasks. In the design section, I hope to show that we developed an operational example of such a system using principles from CSCW and HRI. In the usage section, I presented an analysis of the system's usability and ability to facilitate collaboration between two people. And finally, in the application section, I presented a characterization of some remote settings that involve physical tasks where such a robotic camera solution may be useful. I would argue that this work with Periscope is a step towards building effective robotic groupware, but this term effective is the one part I have not addressed yet. So my understanding of effective through the work in my dissertation is that an effective system is operational, usable, and useful. I'll go through the terms. First, an operational system, I think, is fully functional and high fidelity and deployed in the intended context of use. Many prior works fall short on this aspect, and they're used in very simple tasks and environments that don't reflect the complex real-world dynamics where such systems would be used. Apart from the research contributions, we put in a lot of engineering effort to make our system operational. And I think the fact that our system was operational allowed us to conduct 2-hour evaluation sessions in our first study that gave us this rich and interesting data, and also enabled us to talk to experts from around the country where they could access the robotic camera from their homes or offices. So this expanded the pool of people we could get feedback from for the system. Second, a usable system, I think, should allow users to make meaningful progress on tasks using the provided functionalities. In our lab study, I defined meaningful progress in terms of consistency across people in how they engaged with the system and made progress on the tasks. And usability in HCI and human factors is often defined with respect to one person and the system. But with a groupware system, there are other things that affect a user's experience. Like in our studies, we found that people's perception of the system was influenced by how much they liked their collaborator, for example. And it changed over time, for example, once they had new social norms that they had established with their collaborator. And finally, a useful system, I think, is capable of addressing the needs of a real-world use case, like how instructors were able to successfully use Periscope to instruct students in our lab. Our findings about usefulness are not based on quantitative metrics like perceived usefulness scale. And I think that approach is unreliable in our case because we found two extremes of participants. Either they're really enthusiastic and think everything about the technology is cool, or they focus on one specific weakness and then they can't imagine the system being used at all. So how I'm trying to define usefulness is by breaking down the characteristics of the system and the task and see if it aligns with the current practices and context of our participants. Yeah, that ends the evaluation of my thesis. I'm going to talk about some challenges and future work now. I've alluded to many challenges throughout the presentation, but I'm going to consolidate them into three categories that I think are general challenges in building any effective robotic groupware: arbitration, evaluation, and development. In the example where we saw the robot-led mode was being used, but the worker was explicitly directing the view, it doesn't really align with the idea of this mode being robot-led. It seems like the worker is in charge. But then we also have this other use pattern, which more resembles robot-led mode, where the worker is often unaware that they're even being tracked. So in the next version of the system, we should probably split this mode into two types of arbitration based on the level of contribution of the worker to the pattern of use. The next challenge is evaluation. We need rich data to understand the nuance of how people collaborate using such systems, but these interaction traces are also really elaborate and tedious to interpret. So an added challenge is that it's really non-trivial to translate the insights into actionable changes within the system. And that brings us to development. The development process for groupware has to be iterative because new features can unpredictably interact with existing features, and small changes in the system can cause disproportionate changes in group dynamics. So I've been thinking about whether we can represent the behavior of such systems, especially the arbitration part, which is what needs to be iteratively refined, in a better way that lends itself to quick and iterative development of such systems. We have a concept paper on this where we break down the development cycle into 6 stages, and we talk about how a mathematical modeling language called PetriNets could be suitable as a representation that unifies all these stages of the development cycle. In the paper, we also talk about the challenges with arbitration and evaluation that I mentioned earlier, and hypothesize that PetriNets might be able to resolve some of these challenges. We're in the process of developing a research tool to model HRI groupware using PetriNets, and hopefully reach that vision at some point. Okay, so this is the last part of the talk. So if we were to extend Periscope, what might that look like? I'm going to add some graphics to the slide. They are a little bit blink it and you miss it, so follow along. Okay, so one expert might assist 2 workers. Each worker is co-located with the robotic camera. When a worker has a question, the expert can actively use the robotic camera to assist the worker. The robot for worker 2 takes initiative at this point and monitors the worker on the expert's behalf. if worker 2 now has a question that the expert is required for, then the expert may choose to switch and help worker 2. So in this paradigm of work, what is the role of the robot? Because during the interaction, it changed from being a tool that was being remotely operated to being the expert's deputy and monitoring the worker. What kind of cognitive demands does this paradigm of work place on the expert? Helping 2 workers in the same room is different from helping 2 workers in 2 different places, maybe doing 2 different tasks. Let's consider other modalities. The expert can wear a head-mounted display to see the view, maybe even a virtual reconstruction of the space. What kind of tasks are better done on a screen interface, and what is better done in a 3D environment? Maybe the robot has the ability to grab and manipulate objects. Now, the same robot platform is used for 2 tasks, to show the view and to grab things. So what happens if the robot is grabbing something, but the user wants to move it to see something different? How should arbitration be designed in this case? The robot could have the ability to move around. How does this change in form factor change the types of context that this robot can support collaborative work for? What type of context can we support if the expert has access to a co-located robot, and maybe remote workers can access this robot as well? How can we leverage data collected from such interactions to build better task models, which can hopefully lead to robots facilitating such collaborative work better? Trying to answer these questions I posed are probably going to require new algorithms, representations, methods, and metrics that can help us move towards effective robotic group work. So I hope that my dissertation work has laid some groundwork for how we can build such groupware. I do have a couple more minutes of thank yous, if that's okay. Okay, great. Okay, so I'm going to conclude with some thoughts about my contributions and contributions of others to this. So this is my attempt at explaining how this project came together. I believe my personal lens for doing research is a systems approach. I love thinking about the creation and deployment of end-to-end interactive systems, how the pieces fit together, and how the whole can be greater than the sum of its parts. For Periscope, I created the blueprint of what and how the system will be built and deployed. And on top of that, I designed and implemented the foundational pieces, whether it was for robot motion synthesis or front-end interface or the study design and analysis methods. And then I reached out to people who were experts in specific parts of the projects to help make things better. So this section in the end that is colored differently, that was my exploration of new methods for the evaluation of complex systems, which I hope to be able to refine in the future. So Periscope is built on Danny Rokita's code base, and I could not have explored the questions that I wanted to explore if he hadn't made his algorithms accessible for us. And Haomeng built the front-end interface for Periscope as an undergraduate researcher, and he also took care of all the deployment of the system to the internet. Yipeng was my go-to for soundboarding, for testing, for filling all the gaps in the code base. And Nate's perspective really enriched the study on the remote workforce training. And him being in Madison also meant that I was able to work remotely for the last 10 weeks and spend time with family and friends. And finally, thank you, Sue, for doing an entire side project with me so I could understand the nuance of qualitative analysis, which is the core part of my research methodology. And this is a long list of people I've had the privilege of working with on various projects. And I'm really grateful to have been a part of this. Thank you.